this video, we are going to learn how to perform object detection in Python. And to be specific, we are going to apply YOLO object detections with the use of OpenCV. You only look once YOLO is a state-of-the-art real-time object detection system. YOLO is a deep learning algorithm which came out in May 2016, and it quickly became so popular because it is so fast compared with the other deep learning object detections models. Traditionally, recurrent convolution neural network applies regions to localize the object to perform object detections, which means that the model is applied to multiple regions within an image. And then the model computes scores to an image at multiple locations and scales. High scores regions of an image are considered as an object is detected. On the other hand, YOLO uses a totally different approach. Instead of selecting some regions, they apply a single neural network to the full image and predicts bouncing boxes and probability for each region. These bouncing boxes are weighted by the predicted probabilities. And if the probabilities are higher than the threshold that can be set by the users, the object is considered as detected. Since it only scans the image once to make the predictions as compared to other algorithms which requires multiple scans, it is faster in practice. And that's why this is called you only look once YOLO. The latest versions of YOLO is YOLO version 3. YOLO version 3 uses a few tricks to improve the training and increase the performance, including multi-scale predictions, a better backbone classifiers, and few more minor techniques. This recent version is more powerful than the basics YOLO and also the YOLO version 2. And in this video, we are going to apply the YOLO version 3. YOLO version 3 is extremely fast and accurate. As shown in the picture, in mean average precisions measured at 0.5, YOLO version 3 is about 4 times faster than the other algorithms. Also, you can easily trade off between speed and accuracy, simply by changing or selecting the size of the models without retraining the models again. Our inputs can be in 3 forms: image file, Webcam feed, video files. And with the use of the pre-trained YOLO models, it can detect up to 80 objects, such as person, bicycle, car, motorbike, aeroplane, bus, and etc. If you want to know more about that, you can refer to the COCO files for details. And we will discuss where we can download the files later. Before we move on, I want to introduce a transfer learning concept, which is a very important and interesting benefit of applying deep learning neural network. Because very often we are solving a different but yet somehow similar problems. To take advantage from others' work and to speed up our training process, we usually can reuse partly or wholly from others' pre-trained network to accelerate our own training and solve our own problems. In deep learning, this concept is called transfer learning. This means that we're using the weights in one or more layers from a pre-trained neural network model in a new model. By keeping the weight and fine-tuning the weight or adapting the weight entirely when training a new model. In YOLO, we are applying similar concepts. We will simply download the weight and configurations of YOLO, and download the name file, which is called COCO, and use the deep learning framework in OpenCV that is compatible with YOLO. The advantage of that is that it works without the need to install anything, except that we need to install OpenCV. And one friendly reminder is that the versions has to be at least 3.4.2. So first of all, we can visit pjready.com to download the weight and configuration files. There are 5 models that you can select based on your preference. Say for example, if your concern is about speed, you can pick the highest frame per second FPS models that is Yolov3 tiny. But if you want to have a higher accuracy, you can pick Yolov3 416 or Yolov3 608. The weight file is the training models, and which is the core of the algorithm to detect the objects. And the configuration files, CFG files, is the settings of the YOLO algorithm. And then we can download the name file from GitHub. The name files contains the name of the objects that the YOLO algorithm can detect. In other words, it contains the 80 objects names. The files contains the labels of the classes that the pre-trained models can classify. And finally, we can simply open a terminal to pip install OpenCV Python. And then we can put everything inside a folder that contains the program that I'm going to walk you through. And we are all set and ready to start now. First thing first, we need to import the CV2 and also we need to import the NumPy as MP. So first of all, we also need to load the YOLO weights configurations and also the object names. So everything is under the same folder as shown in the slide deck that I showed you before. OpenCV provides a functions to load the weights and configuration files without the need to convert them. So this is very convenient and you don't need to analyze or write your own loading functions. And the functions will return a model objects that we can use later on for predictions. So first we just create a variables called net and then use the OpenCV function, cv2.dnn.readnet, and then pass the Yolov3 weight for it, and also pass the other parameters that is the Yolov3 configuration file. And that's it. So now this network contains the YOLO Wi-Fi weight and also YOLO Wi-Fi's configurations. So the next things that I'm going to do is to extract the objects names from the Coco file and put everything into a list. So let's create a list first that is called the classes, and then with open, I just open the Coco name files, and we are going to read everything inside this file. So I just use the R as F and put everything inside the classes. So we just use the dot with dot split lines functions. And now we just load the networks and also load all the objects names into this Python program. We can print out the classes to see what's inside this classes list. And so you can see that we just extract the object names and put it inside these classes that contains the person, bicycle, car, motorbike, airplane, and so and so. And that should add up about that should add up to 80 objects names. So after loading the network as well as the objects names, so we are ready to load the target image that we want the network to help us to do the object detections. So right now also use the OpenCV function imWidth to load the image. I already have an image called the image.jpg, and then we can extract the height and also the width. that will be used for the scalings for the after the object detections. Let me show you the image that we have. I am show image img and wait key 0 dot destroy on Windows. Okay, let's take a look on the image first. In this image, there are 3 persons on the left hand side, and there are 1 person on the right hand side, and there are 2 computer, 2 notebook, and there are few plants, 1 cup, and also there are 2 chairs, and also there are 1 bicycle. And let's see how many objects that can be detected by with the use of Yolov3. So once we have the image, we load the image, and we then need to prepare this image and convert it as an input image that can be fit into the Yolov3. So first thing, we need to resize the image in a square 416 by 416 image that fits the size of the Yolov3. And also we need to normalize it by dividing the pixel value by 255. And the values are also intended to be in RGB orders. If because but right now the image is a BGR ordering, so we need to swap it. So here we need to prepare the image called the blob. So by using the cv2.dnn.blob image blob from image function, we first input the image. The second parameter is the scaling. That means that that's what I just mentioned, that we are going to normalize it by dividing the pixel by value 255. And then the size of the image is 416, 416. And then we are not going to do any mean subtractions. So we are going to put a 000 here. For the swap RB, because we are going to convert the BGR image into a RGB orders. So we need to assign it as a true, and we are not going to crop anything. So we are going to assign false here. So let me show you what we've just done by using the blob from image function. So for B in blobs here, and for N, img blob in enumerate B, and cv2.im show image blob. So the cv2.dnn blob from image functions will returns a blob which is our input image after the mean subtractions, normalizings, and also the channels wrapping. So at the end, you should see there are 3 images that contains the red channel, green channel, and also the blue channels. So in other words, that the cv2.dnn blob from image functions that is used to create a 4D blob that is the format in which the deep learning models accepts as its input from the input image. And then now we can use it as an input to our model saved in the net model. So let's remove these few cooks for the time beings. So as mentioned, our saved model is inside a net And then we can use the set input by passing the blob as the input into this network. So in order to get all the information we need from the predictions, like bounding boxes or predicted classes, we also need to get the output layer's name and then pass the names into the forward functions, which will do a forward pass-through of the pre-trained models. So here we want to get the name first by using the output layer's names with the use net.get unconnected out layers names function. And then we can pass it. We have the output layer. We can pass the name, all of the name to the net dot forward function. So let me repeat. So this set input is used to set the input from the block into the network. And then this get unconnected out layers names function is just to get the output layers names. And then by passing this output layers name into the net.forward functions, we will get the output from this function. So in other words, the net.forward functions is used to run the forward pass and obtain the outputs at the output layer, which we already provide them the layer's name. So now the results and detections are all ready. However, we are not done yet because we want to visualize the results. We need to extract the bounding boxes and the confidences and the predicted classes, which will be stored into different lists. So first, let's initialize the list. So we need to create a boxes list to extract the bounding boxes, and we also need a confidences list to store the confidence. And we also need the classes ID list to store the classes ID, which represent the predicted classes. In order for us to extract the bounding boxes, confidence, and also the predicted classes, we need to create two for loops that help us to loop over the layers output. So the first for loop is used to extract all the information from the layers output. And then for the second for loop that is used to extract the information from each of the outputs. For each of the outputs, that is the detections right here, that should contains 4 bounding box offset, 1 box confidence scores, and 18 class predictions. That means for each of the detections here, there should be 85 parameters. And you can consider that the first 4 elements is the locations of the bounding boxes. And then the 5th element is the box confidence. That is the confidence scores reflects how likely the box contains an object and how accurate is the boundary box. And then also contains the 80 class predictions, the probability of that. And then we can assign a scores variable to extract or to store all the 80 classes predictions that is starting from the sixth elements to the end. And then we want to identify the classes that have the maximum scores or the highest scores in this scores vector. So we use the NumPy argument max to extract the highest scores location, and then we will pass this element to identify the maximum value from this class, which is actually the confidence, or you can consider that is the probability. So let me repeat. So we just create an array that is scores, that is called scores, that is used to store all the 18 classes predictions, and then we find out the locations that contains the higher scores, and then we extract the higher scores and then assign it into the confidence variable, because we want to make sure that the predictions has a confidence that is high enough for us to consider that the object is being detected. So here we can give a if loop if branches here. So if confidence is larger than a certain threshold, here I set 0.5. That means is the probability of or the confidence is larger than 0.5. We will start to locate the boxes. And the predicted boxes contains in the first four values of the detections variables, that is the x, y, w, and h. And x, y is actually the center of the is the center x and also y coordinates of the object, and also the size is actually the width and height, that is w and h. So here we just extract the value. That is the center x equals to integer detection, that is 0, and also the center y, that is the detections, the second element, and then width is the integer, that is the third element, and then their height is actually the fourth element inside the detection. Remember that we normalized the image from with the use of block from image functions before. So right here, these all of the value inside these detections arrays is normalized. So in order for us to scale it back, we need to use the height and width that we extract from the original image. So x, we need to times it with the width, and then y is the height, and then width with the width, and then height with the height value. Because YOLO predicts the result with the centers of the bounding boxes, so we need to extract the upper left corner's positions in order for us to present them with the use of OpenCV. So we need to assign another x that is the center x minus the width divided by 2, y equals to integer center y minus height divided by 2, in order for us to get the positions of the upper left corner. And finally, we simply append all the informations to the corresponding leads. Say, for example, the boxes dot append that should contain the value of x, y, w, and h. And then confidence dot append confidence. And then class ID dot append class ID. That should be class ID. Yep. So now we should have all the informations that we need that includes the bounding boxes, confidence, and also the predicted classes. When we perform object detections, it happens that very often we will have more than one boxes for the same objects. So we will use a function called the non-maximum suppressions to only keep the higher scores boxes. We need to pass 4 parameters into the functions that contains all the boxes, their corresponding confidence, a threshold that we are going to filter box by scores, and a threshold that will be used in the non-maximum suppressions. But first of all, let me show you how many objects are being detected at first. So we have 14 objects are being detected, and then we use the functions called the NMS boxes. The first thing that we need to, the first parameter is the boxes that we have, and then the confidence. And then we need to set the threshold. And this threshold, it would be better for us to set the threshold same as the threshold that we set under this confidence. And then the last parameter is the long maximum suppressions. So by default, we use the 0.4 value. And then we can, and let me show you how many boxes that are redundant and we just get rid of. So let's have a quick count on that. So we have 1 as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We just get rid of the 11 and 12, and then we have the 13. So there are 2 boxes redundant. And finally, we can pass all informations and show them into a picture. And first, we need to assign the fonts that we are going to show in the picture. Say, for example, we just use the tertiary plane, and then we need to assign a color for each of the object detected. So we just use a random color for each of them. And then the colors should be between 0 to 255. That is the color code. And then the length, the size should be the length of the boxes that we have. That is 14. should at least have that. And then because we have 3 channels, so we are going to give a 3 here. That should be this one. Okay, so we will create a for loop to loop over all the objects detected. So that is for I in indexes of flatten. And then we extract the XY coordinate and then the width height from the boxes. And we extract the label from the class ID classes and the corresponding classes ID. And then we extract the corresponding confidence. And finally, we assign the color for them. I mean, for these boxes. So we create a rectangle for this image. The coordinate is XY, and then the size is X plus W, Y plus H. The color code is the color, and then the thickness of the rectangle is 2. And I also want to put the heads on this image. That should have the class name and then the confidence. So the location, we can assign the location at X and then Y plus 20. And then the font, we just assign it at the beginning. And then the font size is 2. And we give a white color for the font. And then the thickness is 2. So let me quickly go through this for loop. So here we just use a for loop to identify each of the objects detected, and then we extract the informations back from the boxes, and then that which contains the locations and also the size of the rectangle that we need to show in the picture. And then on the other hand, we just extract back the classes IDs. However, this ID is just a numbers. So in order for us to show the classes names, we get back to the classes list that we extract from the Coco file names right here. So here that is the classes list. So we get their strength. We use the strength to get back to the labels and then assign it to the labels variables. And then we also extract the confidence and then put it into a string and then assign it to the confidence that we are going to show in the picture. So we randomly pick a color for each of the objects. And finally, we create a rectangle and we also put the texts at the upper left corner in the image. So let's take a look on the results. There are totally 12 objects being detected by YOLO. Here you can see that YOLO can detect the 3 persons right here, but it missed a person here. And there are 2 chairs are being detected, 2 dining tables are being detected, and also their laptops are being detected, and also there are 2 plants are being detected as well as the cup here. However, what YOLO missed is the potted plant here, and the bicycle here, and the person here. But overall speaking, so YOLO's performed a very nice job here. So as mentioned before, our input can be in 3 forms that include the image file, webcam file, or the video files. So the videos or webcam files are just a series of image files that we are going to feed into this YOLO network for the object detection. So let's see how we can do that. There are only few changes that we need to make in order for it to work with our webcam and also a video. So here we use the CV video capture to capture either the video or our webcam. So say for example here I just capture the video and then I just comment the loading image files. So here we should have our webcam ready. Sorry, it should be the video ready. And then I need to create a while loop and then keep most of the code under this while loop. And from the video, we will read each of the frame, and I just name it as an image equals to cap.width. And at the end, we need to release the cap. And also we need to assign a wait key here so that the while loop can be break. Say for example, we use the escape key to break the while loop. And that's it for the changes. Let's see whether it works properly. So that's good. Now we can apply YOLOs for the object detections for 3 types of files. They include the image files and videos files. For webcam file fit, we just need to change these video files into 0, and that should work well. So before we end these videos, let's quickly go through what we've done within these programs. So first of all, we use the cv2.dnn.readnet to read the weights and also the configurations from the YOLO files. Remember that there are 5 types of YOLO files, and you can select the what you want. For say, for example, if you want to have a very fast YOLO performance, you can select the tiny YOLO. And if you want the accuracy, if you want to have a very high accuracy, you can choose the 640 files. And then we just use these OpenCV WinNet functions to with the network. And we also download the Cocoa file and then use this with open functions to with all the classes and put it into the classes list. And we just you can either choose the camera or you can either choose the image files. And then if you are going to use a video file or webcam, we have to put everything's inside a while loop. So here we just capture the videos each of the frame, and then each of the frames we just capture the height and width that we are going to use it scale back to the original image size. And then we use the block from image functions to create an input that we are going to pass it on to the set input function. And then we also need to use the get unconnected output out layers names to get the output layers name in order for us to fit it into the forward functions to get the output layers outputs. And then we create a double for loop in order for us to identify or get the information from each of the identified objects. And when we perform object detections, very often it happens that we will have more than one boxes for the same objects. So we need to use these NNF's box functions, which is actually called the non-maximum suppressions that will help us to only keep the highest Gauss boxes. And finally, we will have our last for loop that will help us to pass all the informations and show them onto a picture or onto their videos. One minor point here is that if you want to keep the color remain unchanged, actually we can put it back outside this while loop. And that's it. Thank you for watching. If you have any questions or suggestions about what we covered in this video, please feel free to ask in the comment section below, and I will do my best to answer. And if you enjoyed this tutorial, you can subscribe my channel, simply like the video, and it is a great support to share this video with anyone who you think would find them useful. And thank you all for watching.